Okay, we reached to chapter 17, talking about solubility. The title is Solubility and Complex Ion Equilibria. I'm just going to talk about solubility. You don't have to be worried about complex ion equilibria. I have eliminated from your PowerPoint slide. So you just focus on solubility. It's basically what you learned from equilibrium. And this is an equilibrium that is going to happen on slightly soluble salts or ionic compounds. So Mx is the general formula for an ionic compound. For a salt, that's the cation, this is the anion. And then it's going to be slightly soluble, not fully soluble. A part of it remains solid, so it's going to change to cation, and it can have a coefficient n to an anion, which can have a coefficient of m and n. The coefficients are just like any other equations. They can be 1 and higher. So you write Ksp since the salt is solid. You do not put it in the equilibrium. So K equilibrium for salts is called Ksp. So instead of K equilibrium, we write Ksp. It's called the solubility product constant, and it would be the product of the cation to the power of its coefficient times the anion to the power of its coefficient. So if you want to write the solubility product constant for these two examples on slide number 8, for Hg2Cl2 and for BHgCl2. Hg2Cl2 has a special type of Hg, which is Hg1, so it's going to be this equation. This is solid, and the cation and anions are aqueous. So Ksp is going to be cation to the power of its coefficient, no coefficient here, and for chlorine, it's going to be to the power of the second or squared. For HgCl2, you have it as, again, solid, so it's going to be Hg positive 2 aqueous plus 2Cl aqueous, so the difference is in their cations. Cl squared. So these are again in the brackets, so they are called molar solubilities. Let's see how we work on the questions regarding the solubility. This chapter and this concept should be really easy since you already know about the equilibrium and how to deal with the equilibrium problems. So we have AgBr, the silver bromide, and it's solid, so it changes to Ag and Br, no coefficients, and we're working on slide number 11. So it says exactly 0.133 milligram of AgBr. For some reason I missed the G in Ag today. Will dissolve in 1 liter of water. What is the value of Ksp? First of all, we know that how to write the Ksp, Ag molar concentration of Ag times Br. So you need to find, this is the mass. So you need to find the molarity first. So it's in milligrams, change it to grams. So it's going to be 0.133 times 10 to negative 3 grams. It's in 1 liter already. So whatever you find, it would be the molarity. Times the, use the molar mass of, this is a gram. You use the molar mass of AGBR, which is, I'm getting it from PowerPoint slides, you might find a little bit more or less, but it's going to be the same. So it's going to be 7.083 times 10 to negative 7 molar. Now you can put them in the ice table. Okay, so this is the molarity. Put it in the ice table. If you do the ice table, since this is solid, it's not going to be in the KSP formula, so you just have the values for, at the beginning you have 0 and 0, and then you don't write anything because it's not going to be entered in KSP. Then over the change, you have x added to each of them. The coefficients are 1 and 1, so it's just x and x. So, and you just found that x, which is concentration of Ag, equal to Br, is going to be, you found it, we're just trying to prove it in this table also. So KSP is Ag times Br, so it's going to be 7.083 times 10 to negative 3 squared, because they're both the same, right? So KSP, you will find it as 5.02 times 10 to negative 13. The solubility product constants are given in a chart. If you need them, they will be given in the exam, so you don't need to be worried. Let's work on another example on slide number 18. Slide number 18, an experiment finds that the solubility of barium fluoride, let's write its equation first. Barium fluoride is going to change to barium. At this point, as a chemistry 2 student, you need to know how to write the equations. So the solubility is 1.1 grams per 1 liter. And we are supposed to find the KSP. It's very similar to the other question you had. KSP, according to this equation, is written as concentration of Ba times concentration of fluorine squared. So first, let's find the molar concentrations. It would be a little bit different because of this coefficient 2. It's going to be different from the previous one. That's why you have to put them in the ice table. But first, let's find the solubility in moles per liter. So it's 1.1 grams per 1 liter. 1 mole of this BaF2 is 175.32 grams almost. So the solubilities are going to be 6.27 times 10 to negative 3 molar. This is solid, so we use this for so 0 and 0 at the beginning, then x and 2x are added. So at the end you have x and 2x. Then x, we found it, this is x, is going to be solubility of barium, which is 6.27 times 10 to negative 3. And then for fluoride, it's going to be twice as that, right? 2 times 6.27 times 10 to negative 7, which is going to be 1.25 times 10 to negative 2. 1.25 times 2 negative 22. Now you are ready to plug into KSP equation. So KSP would be 6.27 times 10 to negative 3 times 1.25 times 10 to negative 20, negative 2. Then KSP at the end will be 9.8 times 10 to, I'm sorry, I missed the square because that's a square here. 9.8 times 10 to negative 7 for the value of KSP. Okay, very straightforward, giving you the molar concentrations or solubility in grams per liter, and asking for KSP. You can do it vice versa, finding molar solubility from KSP. The question given is on slide number 22. Calomel, whose chemical name is mercury 1 chloride, was once used in medicine. It has a KSP equal to 1.3 times 10 to negative 18. It shows that KSP is very low, so the solubility is very low. What is the solubility in grams per liter? And the equation will be Hg2Cl2 Hg2 positive 2 plus 2C. This is the first equation you worked on. So KSP is Hg2 Cl squared, right? Then if you put it in the, let me write KSP here because I need the equation for the ice table. So during the change in initial, you have 0 and 0 initial condition, and during the change you have x added and 2x added. So at equilibrium you have x and 2x. So let's plug them in here because you need to find the molar concentrations. So KSP is given 1.3 times 10 to negative 18 is equal to x times 2x squared, which would be 4x cubed. So divide this by 4 and then get the third root. X is going to be concentration of mercury is going to be 6.88 times 10 to negative 7 molar, and then we need the solubility in grams per liter. Now this is moles per liter, so 6.88 times 10 to negative 7 moles per liter, and then use the molar mass of Hg2Cl2, which is 472.086 grams. So moles and moles are canceled. It would be 3.2 times 10 to negative 4 grams per liter. Or if it's asking milligrams, which is optional, I didn't see it in this question, you just multiply it by 1,000. So it would be 0.32 milligrams per liter. It's a very low solubility, and you could imagine from KSP value. Okay, let's move towards the concept check question. The concept check question on slide number 25 is asking for the 3 lead components. You have PbCr04, lead 2 chromate. KSP value is 1.8 times 10 to negative 14. PbSO4 is 1.8 times 10 to negative 8, sorry, negative 8. And for PBS, you have 2.5 times 10 to negative 27. The question is asking to find out which of the following lead-2 compounds would yield the greatest number of lead-2 ions. So if each of them change to lead-2 and the anion, so here we have lead-2 and CrO4, here we have Pb and SO4, and here we have Pb and S. When it says which one forms the greatest number of Pb ions, means which one dissolves better, which one has a better solubility. And the only thing given to you is KSP, so you just go by the largest KSP value. Means the larger the KSP means the more the soluble. So that's how you determine, just without any calculations. The next thing you need to know is what happens if you have a common ion in the solution. You remember the common ion from the previous chapter, when you have one of the components in the mixture as extra from the other substance. So if you have an X then we want to find out if we have extra M or X, what would be the effect on the solubility, which you can predict. We have to use the Le Chatelier's principle to find out the effect of the change. The question on slide number 27 is going to explain it to us. What is the molar solubility of silver chloride? Molar solubility of silver chloride, which is solid. In 1 liter solution, so it's 1 liter solution that contains 2.0 times 10 to negative 2 moles of HCl. So which compound is extra? Because HCl at the same time, HCl is going to change to H and Cl. So what is the common ion? Chloride is your common ion. Okay? So, means that when you build the ice table, you have 0, but do you have 0 of chlorine? No. Chloride? No. You have 2 times 10 to negative 2 moles of it. And moles and molarity are the same because the volume is 1. So during the change you have X and X. Let's put ICE. So at the end you have X and 2 times negative 2 10 to negative 2 plus X for the chloride. So KSP is going to be Ag times Cl, which is X times 2, let's change it to an ordinary number, 0.02 plus X. From the table we have found, and it will be given to you, that KSP value for AgCl is 1.8 times 10 to negative 10. So from this very small value, you can tell that you can ignore X. So it would be 0.02X, then X is going to be 9 times 10 to negative 9 molar. So this X is the solubility of Ag and Cl. If you compare it, so this is the solubility of AgCl in the presence of HCl, which provides a common ion. If you compare it to solubility of just AgCl. The solubility of AgCl without any common ion is going to be 1.3 times 10 to negative 5. So you see, a common ion changes it from 10 to negative 5 to 10 to negative 9. So by adding a common ion, the solubility will decrease. Okay, I told you everything is the same as the equilibrium chapter, so it's time to work on some Q reaction quotient questions. So we can determine if the solid has formed or not. So let's work on some kidney stones in calcium phosphate. Calcium phosphate solid. I have to put the coefficients. 3 calcium plus 2 phosphate with a negative 3. And both of them are equals. So, a sample of urine contains 1.0 times 10 to negative 3 molar calcium and 1 times 10 to negative 8 molar phosphate. KSP for calcium phosphate is 1 times 10 to negative 26. We want to predict, by calculating QC, we want to predict if this kidney stone is going to form or not. So let's find write the KSP, because we know that Q is the same as KSP. Instead of equilibrium, you have the concentrations given to you. So Ca positive 2 cubed times PO4 negative 3 squared. So QC, which is the same exact equation, but these are not the equilibrium concentrations, is 1 times 10 to negative 3 cubed times 1 times 10 to negative 8 squared. So QC is going to be 1 times 10 to negative 25. If you compare this 10 to negative 25 to 10 to negative 26, QC is higher than KSP, so we have passed the precipitation, and this kidney stone is definitely going to form, unfortunately for the patient. Okay, so one more thing that you also had in equilibrium again is when you mix the two solutions, you have to be careful about the new molarities. The question on slide number 34 is telling you that exactly 0.4 liters of a 0.500 molar Pb2 and 1.60 liter of 2.50 times 10 to negative 2 molar of chloride are mixed to form the total volume. V total is going to be 2 liters. Calculate QC and predict if this precipitate will form or not. We know that KSP for PbCl2 is 1.6 times 10 to negative 5. So in order to find KSP, first let's find the write the equation for PbCl2 is Pb positive 2 aqueous plus 2Cl negative aqueous. So QC is going to be Pb times Cl squared. But these molarities are different from these molarities because you have a volume change. So the new value for molarity of Pb is going to be 0.5 molar times 0.4 liters divided by 2 liters, which is going to give you 0.1 molar. And for Cl is going to be 2.50 times 10 to negative 2 molar times 1.6 liter divided by 2 liters. So it's going to give you 0.020 molar. So QC is going to be 0.10 times 00 times 0.0200 squared, which is going to be 4 times 10 to negative 5. If you compare it, 4 is more than, the exponents are the same, so 4 is more than 1.6, so QC again is more than KSP, so this precipitate will definitely form. The last thing you need to know in this chapter is the effect of pH on the solubility. What happens if you add some acid to a salt which is not very soluble? Effect of pH on solubility. And it's easy. Whenever you add the acid to, let me show it. When you add acid to the conjugate base of a weak acid. So conjugate base of a weak acid. When you have conjugate base of a weak acid in the solution, conjugate base of a weak acid is going to be a strong base, right? So this strong base will react with hydrogen ion of the acid, okay? Then pH will affect the solubility of the salt. So on slide number, this is a strong base which is X, so it's going to form HX. So let's work on slide number 38. I will write it here. I want you to have this. It says consider two slightly soluble salts, barium fluoride and silver bromide. So let's find out which one is the anion of the is the conjugate base of the weak acid. This side, we're talking about this side. This is going to form HF, this is going to form HBr, right? I mean, comes from HF, comes from HBr. Which one is the stronger? We said HF, right? HBr is the stronger, so this is a weak acid. So you have to determine the anions come from what type of acid. You just add hydrogen to them. So comes from a weak acid, so F is strong. So by adding some acid to BaF2, you will have some HF plus other products. But by adding AgBr to an acid, nothing is going to happen. So You determine from the salts given to you, you determine which one comes from a weaker acid, and you learn it in the previous chapters. And then you will pick that salt as the one that will dissolve in the solubilities are going to increase. And the very last slide in this chapter, slide number 39, this was a short chapter. KSP for magnesium oxalate is 8.5 times 10 to negative 5. And for CaC2O4 calcium oxalate, KSP is 2.3 times 10 to negative 9. The question is that if you add a dilute acidic solution to a mixture containing these two, which one is more likely to dissolve? Because, okay, well, let's see which one is more likely to dissolve. Now KSP values are given. You need to go with the one with the higher KSP. So the one with the higher KSP means it has more solubility. Alright, you almost knew everything about this chapter from the equilibrium. You just applied it on slightly soluble salts.